Hi, welcome to the video solution for Edexcel IAL Physics. This is Edexcel Unit 2, January 2022, the second video of this part. So let's start. Question number 16. The graphs show how current I varies with potential difference V for a filament bulb and for negative temperature coefficient thermistor. Explain the shape of each graph. Your answer should include reference to movement of conduction electrons in such component. So main idea about filament lamp and thermistor is when you increase the voltage, so current is increased, and increasing current, I'm talking about first filament lamp. So when voltage is increased, current is also increased. And this increasing current will cause a heating effect. Heating. That means temperature of a filament lamp is going to increase. When temperature increases, it causes the oscillation of atom or oscillation of positive ion in the metal to oscillate with larger amplitude. Meaning you can visualize situation. This is a conductor in which we have ions, positive ions, or atom, which in fact are positive ions. These are the ions, and these ions are oscillating continuously. And electrons in metal filament lamp, electron has to pass through between these, and during motion these electron keeps colliding. So more the oscillation, more collision, more the resistance, the higher the resistance. So resistance of filament lamp depends upon the collision, how many collisions are there. So increasing voltage causing increasing current, heating effect causing oscillation to increase, temperature to increase, and due to high temperature, oscillation is going to increase. So these atoms will be oscillating with larger amplitude, and due to which collisions are going to increase. So movement of conduction electron is going to restrict it. That's why resistance is increased. And this is the way that you can explain for filament lamp. And for thermistor, it is something else. When you increase the voltage, of course you have an increase in current, so the heating effect. But thermistor is a semiconductor, and in semiconductor, increasing temperature causing more conduction electron to produce. So higher the temperature, more electrons are produced in the thermistor. So amount of current, amount of charge increase, and current increase. That's why more current flows through the through the thermistor. So resistance is decreased. That's why we have a upward curve due to decreasing resistance for thermistor. So that's how you can write about thermistor. Ultraviolet light of wavelength 20 nanometer is incident on a metal surface. The metal has a work function of 3.68 electron volt. Electrons are released by the photoelectric effect. Calculate the maximum speed of electrons as they are released from the metal surface. We need to find the speed V. So idea is we are given work function phi 0, phi naught, and we are giving wavelength, and it's all about photoelectric effect. So if you see how can we work on with the speed, the idea is first we are going to find the kinetic energy of emitted electron. So we know that the photoelectric effect equation is E is equal to work function plus kinetic energy. Here we can figure out the kinetic energy of the electron, and this kinetic energy is basically half m v square, and this is the v speed that we need to find. So we need to first figure out energy of incident photon with that wavelength. So you can start your working from this step. energy is equal to H multiplied by F, or energy is equal to H C by lambda, because F is equal to C upon lambda. Now you can substitute your number. E is equal to H 6.63 10 to the power minus 34 into C, speed of light, 3 into 10 to the power 8 divided by wavelength 20 nanometer into 10 to the power minus 9. So energy of incident photon will be 9.95 into 10 to the power minus 18 joule. Then EK, kinetic energy of emitted electron, will be E minus work function. So E is 9.95 into 10 to the power minus 18 minus work function, which is 3.68 electron volt, 3.68 electron volt, but this is electron volt, we need to convert into joule, times 1.6 into 10 to the power minus 19. So kinetic energy you can find as 9.86 into 10 to the power minus 18 joule. So this is kinetic energy, and now half mv square is equal to the kinetic energy, which is 9.86 into 10 to the power minus 18. Clearly, you need mass of the electron, which is given in the formula sheet. First, we are going to rearrange. So V would be equal to twice of 9.86 into 10 to the power minus 18 divided by mass, and mass of the electron given in the formula sheet, 9.11 10 to the power minus 31, and we have a square, so we can take the root. Once you solve that, so velocity of the electron will be 4.53 meter second minus 1. A student suggests that if the wavelength and intensity of the light used are both increased, the maximum speed of the electrons released from the metal surface also increases. Explain whether the student's suggestion is correct or it is incorrect or wrong. What are we doing in the question? They are saying that wavelength and intensity, if both are increased, then it is expected, as per suggestion, speed should be increased. Remember, speed of electron, speed of emitted electron depends upon energy of incident photon. Depends upon energy of incident photon. And energy depends on frequency. HF, as you see here, HF, or energy is inversely proportional to the wavelength. So wavelength increased, energy decreased, energy of incident photon. So electron will receive less energy. So instead of increasing speed of the electron is going to decrease if wavelength is increased. Secondly, intensity. There is no effect of intensity on energy of incident photon. If you increase the intensity, then only number of emitted electrons are increased with the same energy, because intensity increase in intensity causing only number of photon to increase, so more electrons are released with the same amount of energy. So no effect of intensity on the speed or energy of the photon. This is the effect of wavelength, and this is the effect of intensity. So increasing wavelength causing decrease in energy, so the speed is decreased, while increasing intensity has no effect on energy, so the speed remains the same. So student suggestion is incorrect or wrong. A teacher has a laser pointer. The laser pointer emits a narrow beam of plain polarized light. Describe how the teacher can demonstrate that the light from the laser pointer is plane polarized. So a student can use a polarizing filter. So this is a polarizing filter. And if plane of polarizing filter is parallel to the oscillation, like this is the laser pointer, and this laser pointer is emitting laser light with suppose in this diagram I'm assuming that it is a vertically polarized, suppose, then clearly these vertically polarized light can pass through the filter and it will come out. So if there is a screen, we will see the spot of laser light, maximum intensity, and this filter then can be rotated in either direction, in each one clockwise or anti-clockwise. As the filter starts rotating, we will observe that the intensity of this spot starts decreasing because filter plane is not parallel to the oscillation. So of course it is it's going to decrease until the filter is rotated to 90 degree. If filter is at 90 degrees, so I imagine this is not there, then filter is in this form, in this shape, 90 degree. So the filter plane and the plane of oscillation is perpendicular, so no light is passed, so we will have no light. So intensity decreases as you rotate the filter, and that teacher can use. Let me erase this so that you can read. Part B, the teacher shines light from the laser pointer onto a diffraction grating as shown. This produces a diffraction pattern on the screen. So we have a first order, central order maxima, laser light, diffraction grating screen. The diffraction grating equation is n lambda equal to d sine theta. State the quantity represented by d. So d is basically called grating element, or this is the distance between two consecutive or two successive slits or two successive grating. Meaning in diffraction grating we have a number of lines, something like that. So we have many lines, something like that, hundreds of, and d is distance between two consecutive slits, d. The teacher made the following measurement. The distance from central maxima of the first order maxima is 1.61. The distance between from diffraction grating to the screen is 2.74. The wavelength of the light is 532 nanometer. Calculate the number of lines per millimeter. We need number of lines per millimeter, okay, on the diffraction grating. So this is the situation. The idea is we need to find d, and we know that d sine theta is equal to n lambda. So we need lambda, which is given, n is 1, first order, n, and sine theta. So we need theta here, and this theta is this. So in order to find that theta, we are given 1.61 and 2.74. So we can use tangent theta. So tangent theta is equal to 1.61 divided by 2.74. So theta is equal to 30.4 degree. Now we have a theta. I can use d is equal to n lambda over sine theta. So D is equal to, N is 1, lambda is 532 nanometer divided by sine 30.4. So D is equal to 1.05 into 10 to the power -6 meter. So this is grating element, distance between two successive line. So if you do 1 upon D, that means 1 upon 1.05, 10 to the power -6. So your answer will be 9.52 into 10 to the power 5 per meter, meter inverse. That means these are number of lines in 1 meter. So you can divide this by 1000 to find number of lines per millimeter, or if you have some, meaning the last step is we need to divide this by 1000 so that we can have number of lines per millimeter. But if you still have a confusion, so this number is basically showing that we have 1 meter contains 9.52 into 10 to the power 5 lines, or grating, or slits. So that means 1000 millimeter contains 9.52 into 10 to the power 5 lines, because 1 meter equal to 1000. What about 1 millimeter? So 1 millimeter will contain 9.52 into 10 to the power 5 divided by 1000. That's why I was saying that divided by 1000 lines. So if you do that, your answer will be 9.52 into 10 to the power 2. That means 952 lines per millimeter. That's what you need to find, number of lines per millimeter. So 952. Using the diffraction grating, the laser pointer, only the first order maxima and the central maxima are produced. Explain how teacher using same laser pointer, same wavelength, could improve his value for number of lines per millimeter. Now clearly if you see, number of line depends on, because lambda is same. So number one factor that can be, change, or we can improve D by changing theta. Changing theta in the sense that instead of measuring this angle, if we measure angle from the lower first order, because this is diffraction grating, we have a two-sided maxima. So instead of this angle, if we measure this angle from the lower first, negative first value, to the positive one, if we measure this angle, then of course theta will be greater. If theta is greater, so percentage uncertainty will be less. D can be improved. Also, we know that there is a screen distance also involved. So if you increase the screen distance from the diffraction grating, higher the grating distance or greater the screen distance will reduce the percentage uncertainty. So the number of lines measurement can be improved by by measuring the larger theta and increase the screen distance. Question number 19, a student carried out an experiment to determine the resistivity of a nichrome wire. Her circuit includes an ammeter, voltmeter, and a variable resistor. Complete the circuit diagram for this experiment. So we need to attach a power supply, ammeter. Okay, so you start with the nicrometer. The idea is we connect every instrument in a closed loop except voltmeter, because voltmeter always connected in parallel. So start with the power supply. You can take a power supply here. And then you can connect it with a variable resistor. And then you can connect with ampere meter. So this is your complete circuit. If you wish, you can put the key or switch, or it's fine. And the voltmeter is left. Voltmeter always connected parallel to the component that you are investigating or you are studying. And you are studying nichrome wire, so voltmeter is connected parallel to the nichrome wire. This is the circuit. The student varied the length of the nichrome wire in the circuit. For each length, she measured the potential difference across the nichrome wire. She used the variable resistor to keep the current in the wire 0.2 ampere constant. During the experiment, the student plotted the graph of potential difference against length. So we have V against length. Determine the resistivity of nichrome. Cross-sectional area of the nichrome wire is this. We need to find resistivity. So the idea is the resistivity is rho is equal to resistance area divided by length. And we are not given anything about the resistance, but the resistance can be replaced with the help of Ohm's law. R is equal to V by I. And why are we doing that? You can see that if you replace R with V upon I, so resistivity will be equal to V upon I into area over length. Now look at this voltage and length. Voltage upon length, this thing. Now look at the graph. This is voltage and this is length. If you find the gradient of this line, then gradient will be voltage upon length. That means resistivity can be found by multiplying gradient with area in divided by current. So we need to figure out gradient first. And for gradient, we need to choose 2 points. This is a straight line passing through origin. The easy 2 points. 1 point is origin. And the next point I can use is, this is the best point here. So this is my X2. And this is my 1, 2. This is my Y2. And this is my X1, Y1 origin. So I can find the gradient using these two formulas. So this is 3.567. So gradient is 3.7 minus 0 divided by 0.9 minus 0. So gradient is 1.09. It's not 1.09, 4.1, yes. 4.1 volt meter inverse. Now we have a gradient, we can find resistivity. Resistivity is gradient, which is 4.1 times area given as 5.3. 5.31 10 to the power minus 8 divided by current, which is 0.2 ampere. So resistivity is 1.09 10 to the power minus 6, or you can say 1.1 into 10 to the power minus 6 ohm meter. This is the resistivity. Now you need to find the power. Straightforward, power is equal to voltage into current. We do not have voltage. We are giving only length. So we can use the graph and we can find the voltage corresponding to that length, 0.75. So 0.7, 0.8. This is 0.75. and here is the 0.75. So voltage corresponding to 0.75 is 3.1. So at length is equal to 0.75 meter, voltage is 3.1. So power would be equal to 3.1 times 0.2. Power is equal to 0.62 watt. Question number 20. A smart meter collects information about the use of electricity in the home. This information is transmitted to the electricity company using radio wave. A typical smart meter emits radio wave with a power output of 1 watt. An intensity of radiation greater than 4.5 watt per meter square or meter minus 2 is dangerous to the people. A person stands 25 centimeter away from the smart meter. Deduce whether radiation emitted by this meter will be harmful or dangerous to the person or not. So we clearly only calculate radiation flux at 25 centimeter and compare with this. So because this is the safest one, so let's calculate. Now this is the minimum. Greater than that is dangerous. This is minimum. So we need to find flux. So flux is F is a symbol generally we use, or you can use I as well. F is equal to power divided by distance. Power divided by area. So power is 1 divided by area. So the person is standing 25 centimeter from the source. So this is the source of radiation, and it is emitting in the form of a sphere, the radiation. That's what we assume. And person is standing there. This is 25 meter distance. So of course area, we need to use area of that sphere at 25 centimeter. So 1 upon area, which is 4, area of the sphere, 4 pi r square or d square. Distance is 25 centimeter. Need to convert into meter always. So 0.25 meter square. And if you use that, then F is equal to 1.27 watt meter minus 2. So 1.27 is less than 4.5. So it is safe. So it's not dangerous. It is suggested that the energy per photon could be important in determining if the radiation emitted by the smart meter is dangerous. The smart meter transmits radio waves of frequency 902 megahertz. Calculate the energy per photon in electron volt. Again, energy of photon, E is equal to HF. So H is 6.63 10 to the power minus 34. Frequency is 902 megahertz 10 to the power 6. So energy that you will find is 6.98 into 10 to the power minus 25 joule, and we need to give answer in electron volt. So 6.98, I guess this is not 6, this is 5. So energy is 5.98 into 10 to the power minus 25 joule, and this joule needs to be converted into electron volt. So 5.98 10 to the power minus 25 divided by 1.6 10 to the power minus 19. So answer E will be equal to 3.7375. 7375 10 to the power minus 6, or you will round it off 3.74 into 10 to the power minus 6 electron volt. This is energy of that photon. The display of the smart meter in one household is shown. This shows the total electrical energy used in one day. 6.85 kilowatt hour. 1 kilowatt hour is the unit of energy equivalent to 1 kilowatt hour is used for 1 hour. The kettle in this house has a power 1200 watt P, and the kettle takes 125 second T to heat or boil the water. The kettle then switch off. Okay. A student suggests that boiling the kettle once uses less than 1% of total electrical energy. So shown by the on the smart meter display. Assess the student's suggestion. So we need to find whether the energy used by that energy used by that kettle is less than 1% of the total. That's what we need to find. So first we find how much energy is used by the kettle. So energy used by the kettle is E is equal to power times time. And power is 1200 and time is 125 second. So energy used by the kettle will be 1.5 into 10 to the power 5 joule. So this is the energy used by the kettle. And now the total energy for one day that is given. So total energy is 6.85 into, because kilo, 1000 into 1 hour, 3600. So the total energy used is 2.47 into 10 to the power 7 joule. This is the total energy, and we need to find how much percentage of the total energy is 1.5. So let's say I'm just using easy comparison. So I need to find X percent of total energy. 2.47 into 10 to the power 7 is equal to 1.5 into 10 to the power 5, and you find X. So X percent would be, if you divide 1.5 with 2.47, you have answer 6.07 10 to the power minus 3 divided by 100. So X is equal to 0.607%, and clearly this is less than 1%. So of course student suggestion is correct. Suggestion is correct or okay. A recorder is a musical instrument with the mouthpiece at one end, as shown. Mouthpiece and open end, and when a musician blows into mouthpiece, a stationary wave is produced in the air column inside the recorder. The stationary wave has antinode at both ends of the air column, as shown. Calculate the frequency of the sound produced by this stationary waves. Speed of the sound is 330. Length of the recorder is 23.6. So a typical question of stationary waves, this is antinode, this is node, and this is antinode, and we need to find the frequency. We know that distance between two successive antinode is lambda by 2, half of the wavelength. This is lambda by 2. So we can say that lambda by 2 is equal to the length of the air column, which is 23.6 or 0.236 meter. and you can figure out lambda here. So lambda is double of that. So lambda would be equal to 0.472 meter. Now you can find the frequency. Frequency is velocity speed divided by the wavelength, and 330 speed divided by wavelength 0.472. Frequency would be equal to 699.15 hertz. The recorder is made from 3 separate sections that slide together as shown. A musician plays the recorder and produces the same frequency sound as in one. The temperature of the air increases. As the temperature of the air increases, the speed of the sound also increases. Explain how the musician can adjust the recorder to produce the same frequency of the sound. So mainly, if you see the equation, frequency depends on 2 factors, speed and wavelength. So if speed is increased, frequency is proportional to the speed, and frequency is inversely proportional to the wavelength. So frequency, if velocity increase, so frequency for sure is going to increase. But if you need to make frequency same, so you need to compensate this increase in frequency with the change in wavelength. So you need to adjust the column so that the wavelength can be adjusted. So if frequency is in velocity increases, frequency is increases. So that means you have to adjust the wavelength so that frequency return to the original value. So lambda has to increase because it is inversely proportional. And of course you can adjust the length or increase the wavelength by increasing the length of the air column by adjusting these slider in the tube. So wavelength has to increase, so the air column has to increase by increasing the length, adjusting the air column. On a violin, a stationary wave is created when a string is plucked. The violin string has a fixed length, but the tension can be adjusted. Fixed length. When the string is plucked, it produces a sound with frequency of 432 Hz. This string is adjusted to produce a sound of frequency 440 Hz. Calculate the percentage increase in the tension in this string. So we know that the tension in the string is related with the formula speed of the wave is equal to T upon mu. This mu is mass per unit length, which is constant for a given string. So you need to find percentage increase in tension, so make T as a subject. So T would be equal to, if you remove the square, so mu times of V square, and V is the speed. So T is equal to mu, and speed of the wave is F square lambda square, V equal to F lambda. You can rearrange T is equal to mu lambda square F square, and mu and lambda both are constant. They are not changing. Mu is mass per unit length for a given string, and lambda is the wavelength, and length is fixed. So length cannot be changed, so wavelength cannot be changed. So that means T is proportional to F square. Now we need to find percentage increase from 432 to 440. So change in string with respect to the initial value, let's call F1. This is F1 at tension T1. This is F2 at tension T2. So we need to find delta T with respect to T1. So delta T is because F square. So F2 square minus F1 square divided by F1 square. Why am I not using this mu and lambda square? Because I am taking ratio. If I use, then both ratios will be cancelled because these are constant. So now the fractional change is, or the percentage change is, you can substitute the number. So F2 is 440 square minus 432 square divided by 432 square. That means this fractional change will be 0.037 and percentage is 3.73% or 3.7. So 3.7% when you multiply by 100. That's how you can find the percentage increase in tension. 3.7% should be increased. I hope you understood all the question. If you have any problem, let me know in the comment section. May God bless you. Have a nice time.